Many theories can be reduced to theory of quadratic forms. So in these few next videos, we're going to talk about the theory of Hermitian forms over fields. As a setup, let E be a Galois extension over f of degree 2, so it's generated by the square root of some element of f. The Galois group is generated by an element, it's going to be an involution because it's going to have order 2. By Galois correspondence, conversely, if we start with E and then we have an involution on E, then we can look at the fixed field of the involution and then we get a Galois extension E over F. Now let V be a vector space over E, then we can define the notion of Hermitian form and sesquilinear form on V. Now the sesquilinear form takes value in E, and it's not quite bilinear, but it's close. So it's linear in the first variable, right? And it's not symmetric. That's the difference. If it is symmetric, then automatically it's going to be linear in the second variable, but it's not. So S of V comma W is the involution applied to S of W comma V. From this we can deduce that S must be conjugate linear, or some people say semi-linear in the second variable. That is, it preserves addition, that's fine, but scalar multiplication work this way. Now just like how we can get a quadratic form from a bilinear form, we get a Hermitian form from a sesquilinear form in this way. And though the sesquilinear form takes value in E, the Hermitian form actually takes value in F. Now from the Hermitian form, we can get back and recover the sesquilinear form uniquely. Now how does this have anything to do with quadratic forms? It turns out that from every sesquilinear form, we can get a bilinear form viewing V as a vector space on F. So this is a bilinear form taking output in F and linear with respect to F. And conversely, from such a bilinear form, we can also recover the sesquilinear form. It turns out that two Hermitian spaces are isometric as Hermitian space, i.e. over E, right, with respect to this Hermitian form and sesquilinear form, if and only if they are isometric as vector spaces, as quadratic F spaces, right, over F with respect to these forms. And we will prove that in the next video.